Hello everyone. My name is Escrivà, and I am currently a postdoctoral researcher at the National Astronomical Observatory of Japan in Tokyo, and I'm going to present two recent works done in collaboration with Chul Munjo about simulations of ellipsoidal PBH formation and non-spherical effects on the PBH mass function. So first, let me introduce what are PBH. So basically, PBH are black holes that could have been formed in the very early universe without an stellar origin. And currently, PBH are a suitable candidate for constituting a significant fraction of the dark matter, in particular in the so-called asteroid mass range, but they can also explain different cosmic conundra and be a proof of the existence of primordial inhomogeneities in the early universe. And well, there are actually several scenarios and mechanisms for the formation of primordial black holes, but let's focus on the most standard considered one, which is from the collapse of superhorizon curvature fluctuations generated during inflation, where these fluctuations can collapse forming black holes during the radiation epoch after they re-enter the cosmological horizon, if these fluctuations are sufficiently strong. And in general, we always assume spherical symmetry when we do numerical simulations and when we statistically estimate the mass function and the PBH production, but actually why? So let's start by assuming spherical symmetry. So the BBKS paper tell us peak theory for Gaussian random fields, and basically you need large peaks to produce a large fraction of PBH in the form of the dark matter. So we can see this by considering, for instance, a monochromatic power spectrum given by this equation, and where the corresponding curvature fluctuation is given by the sinc profile, where mu corresponds to the peak value of zeta, okay, of the curvature fluctuation. And we can define the height of the peak as a ratio between the amplitude mu and sigma zero, where sigma zero is the square root of the amplitude of the power spectrum, okay? So using a specific statistical methodology for accounting for these peaks and to obtain a mass function and so on, we can obtain, for instance, the left figure, which corresponds to the mass function for different equations of a state. And what is interesting is that the peak value of the mass functions corresponds to value of the amplitude mu very close to its threshold value. You can see in this case is around 10 to the minus 2. Instead, in the right panel, what we can see is the total fraction of PBH in the form of the dark matter. And yeah, so for low peaks, we see that there is a huge overproduction of PBH, which is not consistent and compatible. And if we consider a very, very large peak, we have a very small production of PBH. So basically, we need a sufficiently large peak, in this case around 8.8, in order to have PBH compatible with the dark matter. However, peak theory tells us how likely are non-spherical configurations. So in this case, the BBKS paper tells us that we can make a Taylor expansion up to second order of the curvature fluctuation around the peak value. And in this case, the lambda L, these values are corresponding basically to the eigenvalues of this matrix. And these eigenvalues can be related in terms of the ellipticity and prolongedness of the shape, okay, given by E and P respectively. And the main point is that the most likely configuration actually is not an sphere, but are ellipsoids characterized by an ellipticity and prolongedness of the shape. And peak theory also tells us that there is a specific conditional probability distribution for the ellipticity and prolongedness of the shape once we fix the height of the peak, okay? So, and in this case of a monochromatic power spectrum, the variable nu is equal to chi, okay? And what we can see, which is the important thing for our work, is that for large peaks, the mean values of the ellipticity and prolongedness of the shape given by the solid line basically are very small, okay? And from here, it is generically considered that we can assume a spherical symmetry, no? Because we need large peaks to have a significant fraction of PBH in the dark matter, and as you can see from these figures, the expected values, the most likely values of the ellipticity and prolongedness should be small. But actually, nothing tells us that we can directly assume spherical symmetry is a good approximation. Basically, we need to test with numerical simulations. And the reason is because, as I have shown you in the previous slides, the maximum of the mass function happens for values of the amplitude very close to its threshold. And it's not so clear how a small deviation from sphericity will affect the gravitational collapse if we take into account non-spherical configurations. Okay, and we don't know how the gravitational collapse will be affected, how the threshold will be modified, and so on. And as I said, is in the critical regime where we find the maximum of the mass function. Okay, so basically we need to test with numerical simulations, and this has been the main purpose of our work. So let me introduce the settings. So basically, the BBKS paper tells us the typical profile following peak theory, okay? So the typical profile in this case is given by these three terms. So the first two terms are the ones that we have when we only consider spherical symmetry, and the third term appears when we include the deviations from sphericity, okay, through this function A. And well, we consider monochromatic power spectrum, where the two-point correlation function psi is given by the sign profile, and then we have some statistical parameters given by this for the case of monochromatic power spectrum. And then we consider a perfect fluid that fills the Freeman-Lemaître-Robinson-Walker background, okay, with two different cases of equation of state. So yeah, very briefly, let me explain the numerical method and procedure. So basically, we use 3+1 relativistic numerical simulations with the BSS and formalism. And for that purpose, we use Cosmos code. And as I said, we consider an energy momentum tensor given by a perfect fluid. The algorithm for the fluid dynamics are given by these two papers. We also use a spherical code with a Misner-Sharp formulation to obtain efficiently the thresholds of collapse for the spherical case and also make control test with Cosmos code. The initial conditions are fixed once we fix the curvature fluctuation zeta at super resonance scales. And the evolution equations in a cosmological settings can be found in this paper. Okay, so I skip a lot of details. And let me show you an example of the dynamics of the gravitational collapse in the case of a radiation fluid. And well, this case corresponds taking an amplitude of the fluctuation slightly above the threshold, okay? And we consider an ellipsoidal shape with ellipticity equals 0.08 and prolongedness 0, okay? And the panels show the ratio of the energy density in terms of the energy density of the background. And well, you can observe that initially the shape is ellipsoid, but for very late times, sufficiently late times, the shape is almost spherical, okay? So basically we observe a damping oscillatory behavior of the ellipticity of the shape. This is somehow consistent with non-spherical simulations of the collapse of a perfect fluid in asymptotically flat space-time with small deviations from sphericity, okay, where it was as well observed that the deviation from sphericity decays in time. We also observe that in our settings, non-spherical effects tend to slow down the collapse and significantly increase the collapsing time, okay? And here we have a case with omega, so the equation of state equal to 0.1, so softer equation of state. And what we wanted to test this case because we may expect from the paper of Lim, Mestel, Shaw of ellipsoidal dust collapse case that deviations from sphericity can grow actually in time when we consider sufficiently soft equation of state, okay? But actually, we don't find that. So in our simulations, we have tested, and again, as happens as in the previous case that I showed you with the case of radiation fluid, the initial shape is ellipsoid, but this deviation from sphericity decays in time, and the shape for very late times is almost spherical, okay? So this is somehow against expectation, and then we find that we can expect that only for very extremely soft equation of state, almost near the case of dust, non-sphericities can play an important role in this collapse dynamics, increasing in time instead of decaying as we have seen in our case. So then by performing several iterations with a bisection method, we can obtain the critical values of the ellipticity and prolongedness once we fix the value of the amplitude of the fluctuation mu to a typical value. So in this case, we find that the thresholds are very well described by a superellipse curve given by this formula, where the exponents n plus and n magnus that corresponds to the region of positive prolongedness and negative prolongedness respectively. So in the figure, what we can see is that inside the curves, the deviation from sphericity is not sufficiently large in order to prevent black holes to form. And otherwise, for outside the curves, the deviation from sphericity is sufficiently large to prevent the fluctuations to collapse, forming black holes, okay? So yeah, and something interesting is that we find that both exponents, n plus and n magnus, actually give us very similar values for the two cases tested of radiation and soft equation of state, okay, which is something a priori unexpected. And we wonder if there is some kind of universality in these values of the exponents of the superellipse curve. But we will need much more research to clarify this aspect. And we also may conjecture what is the shape of the critical configuration for the amplitudes following this rescaling in terms of the new amplitude of the fluctuation mu instead of a typical value. Then we have also obtained the behavior of the critical ellipticity, fixing the value of the prolongedness to 0 in terms of the amplitude of the fluctuation. And what we find is that our numerical results closely follow a power-law relation given by this formula with coefficient k and some exponent gamma. And basically, we don't find significant differences between both equations of state. And we may expect only a significant difference for the case of dust or when we consider a very extremely soft equation of state, as I mentioned before, for the case of the dynamics and the decayment behavior of the ellipticity. And basically, we can see that the non-spherical effects from the figure make the collapse much more difficult compared to the spherical case. And we can evaluate what is this effect in the production rate of primordial black hole. So to do that, we can make an integration of the probability distribution of the conditional probability distribution of the ellipticity and prolongedness once we fix the height of the peak. And we can integrate in this domain of integration, basically considering vertical lines with constant value of the ellipticity, okay, and integrate over the domain for different prolongedness values. And well, we can see from this figure that when we consider a fluctuation mu much larger than the threshold of the collapse, for in this case we have rescal in terms of the spherical collapse, what we see is that 100% of the configurations will collapse, forming black holes. So basically the deviations from sphericity are not significant to avoid all of these configurations to collapse to form black holes. Instead, when we approach the critical regime and we consider values of the amplitude very close to the critical threshold, what we see is that a large number of configurations are preventing from collapsing into black holes. Okay, so basically we show and conclude that non-spherical effects are very significant in the critical regime. Okay, however, when we consider just a shift of 1 or 2% in the threshold in comparison with the spherical case, we see that roughly 90% of the configurations will still collapse, forming black holes, okay? And one aspect is, well, the next question is, what is the consequence of that effect for the PBH mass function? So let me show you the final result of the PBH mass function, including non-spherical effects. So first of all, for this computation, we need to know the behavior of the PBH mass in terms of the deviation from sphericity parameters, ellipticity, and prolongedness. In this work, we don't make such a numerical computation, but rather we use existing analytical and numerical studies that indicate that even in the presence of non-sphericities, the black hole mass follows scaling law in the critical regime, okay? And this comes from works where they consider non-spherical effects of the collapse of perfect fluid in asymptotically flat space-time. Okay, so basically we consider that the mass has this functional form where only changes the critical threshold mu that now will depend on the ellipticity, and gamma that only depends on the equation of state. Okay, and well, actually, this plays a crucial role because you can see in the bottom panel the behavior of the PBH mass in terms of the ellipticity, but also the amplitude mu. So now, in comparison with the spherical case, well, we have a region where we cannot form PBH, so basically we have zero mass, and this corresponds to cases where the ellipticity is sufficiently large in order to prevent black holes to form. Okay, that comes from the numerical result that I showed before about the behavior of the critical ellipticity in terms of the amplitude of the fluctuation. And here you can see that the solid lines are the lines that denote constant mass, okay, where this crosses corresponds to the numerical values that we have. So if we take into account this behavior, at the end we find, and you can see in the top panel, well, in the right, that the difference of the mass function between the spherical and non-spherical case is actually very small. Okay, so at least for the case that we have tested of a monochromatic core spectrum, the non-spherical effect is not significant. And the reason is because at the end, although we have seen this remarkable behavior of how the deviation from sphericity affects the production rate of PBH, especially in the critical regime, suppressing a large number of configurations from forming black holes, at the end, the mass function is dominated by fluctuations that are very close to its critical threshold, mu c, where now the new critical threshold includes the deviation from sphericity given by the ellipticity parameter. Okay, uh, for the case that we have tested of equal programmers. Okay, so at the end, the difference in the mass function is very small for the cases tested. Okay, which somehow is against previous expectations, where non-spherical effects were expected that could have played a much more remarkable effect. And well, I give you here with the conclusions. You can read. Of course, there are some other possible future interesting research that can be done, which is what happened with other power spectrum for all of these results that I have shown you, or what happens with non-Gaussianities, where the probability distribution may change and we may expect maybe different results. No, so yeah, I stop here, and if you have any questions, I will be very happy to answer and get in touch with me. Thank you very much for your attention.